Welcome to my video presentation. My name is John Malika, and today I'm here to talk to you a little bit about smart electronics and their role in modern society. To give you a little overview on the presentation today, we're going to talk a little bit about smart technologies. So that means electronics that have multifunctions. We're going to define and describe UBCOM systems, ubiquitous computing systems. We're also going to mention some common smart electronic devices, and we're going to look into smart electronics creating harmonic distortion. So what is a smart electronic? Smart electronic has many functions. You can talk on it as a phone, perhaps. You can access data. You can share this data with other electronic devices. Use applications. Generally, smart electronics are small. The reason for that is because smart electronics need to be integrated into society, and they need to be marketable. And smaller electronics tend to be more marketable and less obtrusive for the general public. They also need to be hyper-communicative. So in this day and age, data streaming, accessing data, these are all key components for smart electronics. And so in order to stay up with the trends, you need to make sure that it needs to communicate with other devices. You also want to make sure that there's a massive applications framework that this electronic can access. So you want to have a lot of information that you can delve into when you use an electronic, so you have a lot of options and functions to work with. Now I'm going to talk a little bit about what a ubiquitous computing system is. This is the framework behind what a smart electronic is. It's kind of like the model, you could say. Now, it's a protocol for all smart devices and what they should strive to become or complete. Now, the idea behind a ubiquitous computing system is complex and multi-layered. So we're going to define them a little bit more in this next slide. Here are some core values for a UBCOM system. They must be networked, distributed, and transparently accessible, which means that ubiquitous computing systems need to make sure they can communicate with one another through a large network. They need to be distributed to be able to communicate from one to another, and transparently accessible, meaning that there's not a lot of barriers of entry when it comes to using the system. Number two, you want to have human-computer interaction that is hidden a little bit more than a general computing device. What this means is that you're not going to explicitly be giving your device commands about what you want it to do. It'll have to do a lot of its own computing background information work on its own. Computers need to be more contextually aware. So this is kind of more behind the idea that a butler knows how to serve you. A butler is going to know what you like and how you like it. Now, ubiquitous computing system is going to be a little bit of the same thing. It's going to be programmed in such a certain way that it's going to understand when you give it a command that it's going to give you a contextual output of that command. So if you search for something specific, it's going to give you a list of specific things that you've searched for in the past, for example. Computers can operate autonomously without human intervention, be self-governed in contrast to pure human-computer interaction. So what this means is that computers do a lot more functions on their own, and you don't tell them as much what to do as they just take care of you. Here's a common smart electronic device. This is an iPhone. It's made by Apple, and here you can see it's disassembled, and all of its components are laid out. There's the battery right in the middle of the screen. Beside it are the cases and some of the microphones and devices as well. Here you can see a few more of the inner workings. Now you can see how small the processor is, the Apple A6 processor, right in the middle. Now that's the brains of the operation, and that houses all the software and does all of the control information for the user. Here's an uncommon smart electronic. This is Kit the Talking Car, a bit of a throwback, but in the television show Knight Rider, he was a bit of a smart electronic device. Here's a hardware block diagram for the iPhone. So here we can see all sorts of different hardware devices that are implemented into the iPhone. You need to make sure that your power is managed, your battery is being run properly. You need to make sure that it can be plugged into USB ports, speakers, earpieces, microphones, all telephone device information. Touch screen needs to work, Wi-Fi and Bluetooth, GPS. These are all functions that have all been implemented and thrown into the same device. All of these have been integrated into this one device to make it work seamlessly. Now, smart devices tend to be a little bit more delicate when it comes to charging. Now, this waveform here shows on the top a steady, consistent sinusoidal current waveform, and on the bottom, that's what the input is for a cell phone charger. Now, you can see how small and how little of the average power that sinusoid is actually delivering to the cell phone. You can see the same in the second example as well. Now, a lot of the time what ends up happening is rectified signals that are delivered to charging devices for electronics create something called a harmonic, and that's an example of power quality that's diminished because of harmonic injection into a system. So, today we talked a little bit about smart technologies. We talked about ubiquitous computing systems, iPhones as a common smart electronic device, and we talked a little bit about harmonics as well. Thank you very much for listening. That was my presentation.